Welcome. In this session, we'll explore a non-convex optimization problem. It'll be non-convex because we'll have a convex objective, but we'll have a non-convex constraint. And what we want to do is explore this idea of constraints and the Lagrange multiplier a little more deeply. So let's consider this. Let's consider a problem where we have, instead of having a squared norm as we had before, let's have a squared weighted norm. And let's specifically say that the problem is we want to find a stationary point for the problem that is the minimizer over all vectors in a two-dimensional vector space of a second function. So this is a second function that has a vector argument. And what we'll specify here is we'll specify that this second function is, our standard form will be 1/2 times the transpose of the argument times a symmetric positive semi-definite matrix times the argument. And we'll have a second property, and the property that we'll pick this time is a non-convex property. And that is, let's say that the first entry of the argument, -3, is squared, and then we'll subtract the second entry, and then we'll add 1 to that. And we'll require for this that the second property at the stationary point for the problem is 0. What we'll do is we'll pick a symmetric positive definite matrix, and it will be a diagonal. So all we'll do is we'll multiply one of these. We can imagine taking one of these entries and we'll multiply it by some value, and then we'll square the whole thing, and that will be our objective. So that will, the level curves for this will be an ellipse. And this property is a little harder to imagine, but what this basically will do is this will be a parabola. And so what we'll want to do is we'll want to try to figure out where an ellipse and a parabola are going to be. So the way that we'll draw this out is this. Here we'll have our standard little graph, and I'll pick a symmetric positive definite matrix. The horizontal axis is the first entry of the argument, and the vertical axis is the second entry of the argument. And I'll pick these so that the level curves are tilted ellipses. And the way that this will appear is this will appear as a parabola that is offset. And we can see that if we increase the levels of our objective function, that as we saw in the previous session, at some place there are 0 solutions. And then at some place there are 2 solutions. And if we increase this, depending on exactly how this is tilted and exactly how this is placed, we could have 0, 1, 2, 3, or 4 solutions to the intersection of a level curve of the objective and the constraint curve. So our problem here is that what we need to do is we need to figure out what is happening when we have these. Now let's write down a little bit of math, because this will help us. Let's observe. So let's observe from this that the gradient 1 form of this function is, so if I differentiate this with respect to w, that if we remember back in those sessions where we derived this, that would be we would basically eliminate this w and multiply by 2. The 2's would cancel, so that would be W transpose times this symmetric positive semi-definite matrix. And if I differentiate the property with respect to its argument, what I will get is that will be 2W1, that gets 2 minus 6, and then there will be that will be the derivative with respect to W1. So let's put a comma there. And then when I differentiate this with respect to W2, that will be a minus 1. So now we can write these down, but this is the algebra, and then this is the geometry. Let's take a look at what happens when we compute all of this. When we do our computations, this is what we'll see, is we can increase these levels until the level curve exactly satisfies the constraint property function. And what we find is that this optimal point for function 2 is approximately these numbers. And this is the geometry behind it. As we drew before, if we pick a small level, there are no intersections. And if we pick a large level, there are 2. And then for some level, there's exactly 1. So we already know how to compute the gradient. That is, given any point, we can compute the gradient of the objective function, and we can also compute the gradient of the property function. And what happens when we insert these numerical values into those two gradient computations? Well, when we transpose them, what we find is that the gradient for the objective is this cyan arrow, and the gradient at this point for the constraint function is this arrow. Now, if we had picked some other place, the gradient would be pointing down like this, and if we picked some other point that was on the constraint function, it might be pointed like that. However, these two gradients, or the transpose of the gradients represented as vectors, are parallel and multiples of each other at this solution point. And indeed, we can compute what that multiplier is, and it's not a nice round value for this example, but it is a unique value.